Three, two, one. All right, so as promised, we'll now speak of ordered fields. So we're getting dangerously close to actually getting to the real numbers. So again, let's take a moment here and really discuss what the set should be. Right, because this is going to be our sort of foundational set that we're going to build all of analysis and thus all of calculus from. So, what should the set be exactly? Yeah. Now, we've already talked about sets in general, and we've talked about ordered sets now. Now, the real numbers should have some things. So, first of all, they need to have the integers, and let's think for a moment, right? I can, of course, just write out all of the integers. There they are. There's all of them. There's no more. um, and right, we could just be like, oh yeah, they got these things, but what do they really have here? What are the integers exactly? Well, right, what is zero? Well, zero has kind of got a unique property, which is that if I add it to anything, nothing happens. One has a unique property in that when I multiply it by anything, nothing happens. 2 is 1 plus 1. 3 is 2 plus 1. -1 is the thing with the property that -1 plus 1 is equal to 0. That's kind of neat. But there are other things that the real numbers should have, which are rational numbers, which are ratios of two integers where the bottom integer is non-zero, right? I, of course, could talk about 1/2, which has the property that 2 times it gives me 1. Right, and so from there we kind of have this idea that the real numbers should have some operations associated with them. There should be these adding and multiplying, but the real numbers also have to have some of our other favorite constants, like square root of 2, pi, and e, so on and so forth. So there needs to be something else to them besides just the pure algebraic ideas here that the integers and the rational numbers possess. There needs to be some way of creating these things, and I bet it's the least upper bound property. All right, but let's talk algebraic properties. So, how do we actually create the real numbers? Well, our goal is to get there. We're not really going to create them. We're just going to say they exist. But what are the things they need to have? So, the things they need to have, as we've already noted, they need the integers and the rationals. So there needs to be some sort of adding and multiplying. So a set is called a field if for each element that lives in my field I have a sum and a multiplication, and they adhere to the following rules. Okay, so specifically, addition needs to do 4 things. Addition needs to be associative, right? Note the way addition is defined is give me x, give me y, I can make their sum. Well, after I make that sum, I can keep adding stuff to it, and associativity says it doesn't matter how you group those terms together. If I have x, y, and z and I want to add them up, I can do x plus y and then add z, or I could do y plus z and then add x. It has to be commutative, meaning that it doesn't matter the ordering in which I do it. If I do x plus y or y plus x, nothing changes. There is an element in the field that addition does nothing with. Specifically, if I add by this element, which is usually referred to as the zero element, nothing happens. And when I'm talking about fields in general, I will do the subscript f to indicate that it's the zero element of the field. Some people don't do that, but I don't like that because 0 is the number 0. Sometimes they'll bold it or something. I like to include a notation to indicate that what I have here is the 0 element of my field. Right, and then also we need to have additive inverses, meaning that for every element in my field, there's something I can add to it that gets me back to 0. Okay. So this is just basically saying that addition should work the way we've always done addition. Addition should work with the way that you intuitively have always worked with addition. Okay, and again, as usual, now that we've instilled a new construct here, let's make some points of order, which I'm a fan of doing. Okay, so one of the features of the associativity property is that I don't need to include parentheses when I'm talking about addition by itself. When we start mixing in other operations, then you better be being careful with your damn parentheses. But if I'm just talking about adding up like 15 things, it doesn't matter. You don't need to include the parentheses. That being said, though, we'll still include brackets and parentheses when we need to put emphasis on something, right? Because sometimes when we add up a bunch of stuff, we want to focus in on part of it and go, hey, this is kind of neat what's going on right here. So we will include parentheses when needed. Commutativity will be used whenever we want without reference. So, for example, our assumption was that x plus the zero element gives you x. Commutativity allows us to then infer that this needs to be true, but we'll just freely use commutativity in the same way that we'll just freely use associativity. All right, we'll use the phrase non-zero whenever you're not equal to the zero element. And as is tradition, subtraction is not a real thing. What is real is adding the additive inverse of something, and it's typically written as x minus y. All right. Okay, so now that we've set up the basic axioms for addition, and we've talked about some notational things we'll do with them, before we get to how multiplication works, let's actually prove a couple of things about how addition works. And again, the goal here is not to be exhaustive. There are plenty of other theorems about addition that are true, but we want to get a feel for them and prove, in my opinion, what are some of the more pertinent things. So the first one is that cancellation is allowed. So if I know x plus y is equal to x plus z, then I can conclude y is equal to z. If I know x plus y is equal to 0, then y has to equal negative x. So in other words, not only do inverses exist, they have to be unique. And then finally, the negation of a negation gets you back to normal. All right, and it's worth noting there's, again, plenty of other theorems that you can establish here, but we'll go ahead and just prove a few to go that, hey, in a field, addition works the way you think addition should work. And then whenever you've got a thing that you're like, oh, I'm pretty sure I can additively do that, you can sit down and write out the proof of it. So I'll give you a couple of examples here so you get a feel of how you should write proofs involving things with additions in fields. Okay. All right, so indeed, I want to show that y is equal to z, and what I know is that x plus y is equal to x plus z. Now, intuitively in your mind, you just go, oh, well, subtract both sides by x. Okay, but again, like I said, subtraction isn't a real thing. So if you actually want to prove this, here's what you need to write out. And let's be very careful to point out all of the assumptions that we're using, all of the axioms of fields that we've established. So we start off by noting that y is equal to the zero element plus y. The zero element is equal to this. So I've used the properties so far of what the identity element does and what inverses do. And now note here that this is valid because of associativity. And this is equal because this and this are equal by hypothesis. So I have used the existence of an identity, the existence of inverses, and the associativity. Cool. So note, I used pretty much everything but the commutativity here. Note the commutativity allows me to do cancellation on the right as well as on the left. So by commutativity, I know y plus x equaling z plus x. I could then cancel the x's and get y is equal to z. All right, beautiful. All right, now that we've proven that, let's use it to verify point 2, because x plus y equaling, oh, and it needs to be the zero element in the field, not the number 0. Just saw that. How many of you saw that and were, like, screaming? Probably none of you. Maybe somebody noticed. I'd be like, oh, hey, then you just make a whole spiel about how... Yeah. All right, got it. All right, anyway, so in point 2 here, if x plus y is equal to the zero element of the field, well, that's equal to x plus its additive inverse. And hey, I'm allowed to cancel, so I get that y is equal to negative x. Beautiful. And specifically, point 3 also follows from point 2, because negative x plus x is equal to the additive identity. So replace y here with x. And replace x with negative x, and you get this. So if you negate the negation, you get back to normal. Beautiful. Alright. Alright, so that takes care of some facts, additive facts. So again, this is not exhaustive. There are more, but anytime you think of one or want to use one, you can formally prove it and then use it. Alright, so let's now talk about what multiplication should do. And multiplication, very similar to addition, needs to be associative, it needs to be commutative, it needs an identity, but it's worth stressing that what I have cannot equal 0. Otherwise, things will be very boring. If 1 is equal to 0, then nothing's going on. So again, this needs to have the property that when I multiply by it, nothing happens. And inverses need to exist, but as we know from intuition, 0 cannot be part of the conversation of things that have a multiplicative inverse. Right, division by 0, right, we know is not a thing that we should allow. Although, when you take Math 301, it turns out you can allow division by 0. In fact, you can divide by 0 in the world of matrices, but it's, yeah. Not for us. Alright, now, so far know that these are all just sort of the analogous rules from addition. Right, that multiplication is associative, commutative, has identity, and has inverses, appropriately defined on the inverses there. The other thing we need is that addition and multiplication need to interact with each other appropriately, and that's the distributive property. So if I multiply a summation, I'm allowed to do the multiplications and then the summations. So note, distributivity here is also kind of asserting an order of operations, right? A PEMDAS, if you will. So that when you want to multiply a sum, what you really do is the multiplications first, and then do the summation. Alright. Now, again, there are some conventions in terms of notations and how we'll use this stuff, so let's point them out. So something that we do in multiplication a lot is just not write it. So, yeah, just x times y. So that happens quite a bit, and right, we're just lazy. But right, when you think about it, when you write 2 times x, yeah, you just write 2x. So we got that. 1 over x. So note, some sources will write this as x to the negative 1. But I've gotten more into the habit of just always writing it like a fraction like this, because again, when I multiply, I want to be able to cancel it. So I always like to write it as a fraction. And as is tradition, the fraction x over y, or x over y written this way, is really x times 1 over, is really x times the multiplicative inverse of y. So again, division's not a real thing, it's just multiplying by the multiplicative inverse. Okay. So, similar to addition, there are a bunch of multiplicative facts that are true, but for our purposes, let's just prove a few, and again, this is just to get a good feel for how this stuff should work. Alright, so the first thing that we'll prove is that multiplying by 0 is what you think it should do, which is, it just gives you 0. And why is this true? Well, it turns out this follows from distributivity, because if I look at 0 times x plus 0 times x, well, I can factor out the x here by distributivity. I'm allowed to do this. And 0 plus 0, well, that's the additive identity, so that just gives me back 0. And now I can cancel and get that this has to actually equal 0. Beautiful. So, the fact that 0 times anything gives you 0 is actually a consequence of distributivity. Kind of neat. Alright, beautiful. Alright, so next up in a field, we'll prove that if you've got a product equaling 0, then one of the things needs to equal 0, which again, as I've already briefly sort of mentioned, that's not something matrices do, because matrices, right, this is basically saying that division by 0 is not a possibility. Because if you product a 0, the only things that could have worked were zero itself. If you've got a product of non-zero things equaling zero, which you can have on matrices, those things are like technically being divided by zero, you know? So, anyway. Alright, let's verify this. Now, note, this is an OR statement, not an exclusive OR statement. It's an OR statement, and OR in math is inclusive. So if I want to show that this is true, I only need to verify that one of them is true. I don't need to verify that one is true and the other one can't be true. So if I actually want to do this proof here, if I already know x is equal to the zero element, I'm done. Because one of them was true, so the OR statement is true. So I actually can just start off with, well, suppose this is not true, then let me verify this. Well, if that is not equal to zero, then I've got access to its multiplicative inverse, and appealing the point 1, so note, y has to be 1 times y. 1 has to be x times its multiplicative inverse. By associativity, I can move the parentheses over here, and I should put parentheses around that. That looks a little confusing. Where is it? Where is it? Where is it? Where is it? There, right there. Get that multiplication in. Alright. So, just for clarification's sake. Alright, and now by hypothesis this is equal to 0, but as we just proved, anything times 0 is 0. So, if x is non-zero, then it's got to be that y was 0. So if I have a product of two things equaling 0, one of them must equal 0. Beautiful. Alright, and again, note the things that we proved here. We are using the associativity of the multiplication, we are using the existence of a multiplicative inverse, we're using a multiplicative identity, we're using the existence of inverses, and we're using the distributivity. So it's good to keep track of all that stuff and really think about what's being used, where it's being used, blah, blah, blah. Good stuff. Alright, next up on our list, to remind you, we'll prove that multiplying by an additive inverse is what you think it should be. So, read this out exactly. This says that the additive inverse of a product is the additive inverse of x times y. So, I can put the minus sign wherever I want. Or, another way to think about this is saying that multiplying by -1 gives you the additive inverse. Alright, and the proof of that is similar from point 1, where we'll set up a summation, we'll invoke distributivity, and then we'll invoke the facts that we know about what this should equal. And we'll also use the fact that 0 times 0 is 0, so since this sums up to 0, it's got to be that this is that this here is the additive inverse of this element here. And equipped with this, we can then show that if you multiply negative by negatives, now note here, I can pull out one of them, specifically this one, and then by commutativity I can rearrange and pull it out, and as we verified, negative gets you back to normal, and note that I'm explicitly using the commutativity here. Beautiful. Alright, so, there you have it, adding and multiplying in a field, and their basic properties. So again, this is just how addition and multiplication should work. So whenever we're working with real numbers and we're adding and multiplying them, the way they should behave is the way you think they should behave, because the axioms we set up are saying they behave the way you think they should. Alright, but as we noted, there's one more aspect to the real numbers that we need, and that is the ordering part of it. And that turns out to be the thing that makes the real numbers, and not just, the rational numbers or something. Alright, so a field is said to be ordered if it's a field, so it has adding and multiplying, but there's also an ordering running around, and the ordering interacts with addition and multiplication in a meaningful manner. The first one is that if I know A is less than C and B is less than D, then that summation works. And the second one is that multiplying two non-negative things remains non-negative. So those are the two things we need to assume about how addition and multiplication works with orderings. Alright. So, some things to note before we get proven with this stuff. And as we'll see, we're going to prove basically things that you think should be true. But some notational things. So, I always use the phrase positive to mean less than or equal to here. Strictly positive is when we've got the strict one. So I know some people probably wouldn't consider 0 to be positive, but it turns out that it's better to include that and then just reserve strict for strict like this. And similarly for negative and strictly negative. Alright, so let's prove a couple of things involving ordered fields, so we get a feel for how they work. Alright, so first one is an inequality is true precisely if this is true. So in other words, I am allowed to additively cancel across an inequality without screwing up the inequality. Or likewise, I can take an inequality and add whatever I want, and it doesn't mess it up. Note a little bit later on, we'll see that you can multiply, but only if you're positive. So if you're a homework, you're going to prove an equivalent statement for what happens when you multiply by negatives. Alright, so the first two things are basically saying that adding over inequalities works the way you want it to. The next one is revealing that when you negate an inequality, you flop the order. And then we'll prove that 0 needs to be strictly less than 1, and if you've got something strictly bigger than 0, then it's not equal to 0, so it's got a multiplicative inverse, and its multiplicative inverse remains positive. Right, and again, this is not an exhaustive list. There's plenty of other properties. But, right, let's just get a sampling of how some proofs work, because then whenever we need any sort of order algebraic fact, you can explicitly prove it. But again, these axioms are set up so that we're getting, a set with properties that we want them to have. Alright, so let's do the first proof. So suppose A is less than or equal to B. C is less than or equal to C, so by our hypothesis, I have A is less than C, and C is less than C, so the summation must work. So again, remember the way the hypothesis was that I needed these inequalities to be true to get this inequality. Alright, so let's do the converse. Suppose that I know A plus C is less than or equal to B plus C. Well, C's additive inverse is less than or equal to itself, so this plus its additive inverse needs to be less than this plus the additive inverse of C. But again, by associativity, this is well defined, and C minus C is 0, C minus C is 0, so there we go, A is less than or equal to B. Nice. So, again, as noted, a lot of these proofs are just clarifying. They are just going, hey, these axioms are this is how addition and ordering should work with each other. And they're not the most enlightening or juicy proofs, but they are clarifying. And, again, they are worth doing. Alright, so now let's do the strict case. So, for the strict case, we can use the non-strict case, because if this holds, that means A is less than or equal to B, and thus I have this inequality right here. And now if that is equality, then A has to equal B, which contradicts my assumption, so it's got to be that I had strict. And this is something you do a lot. So a lot of times you actually do proofs with less than or equal to, and then for the equivalent strict proof, well, I've got the one for less than or equal to, so the strict one we just get for free by just some minor modifications. Okay, and the converse is not particularly enlightening. It's basically just, hey, do exactly what we just did. But in this case, the contradiction we derive here is that A plus C is strictly less than A plus C. And so again, like I said, in the ordered set video, you'll be shocked how often you actually use that fact that nothing is strictly less than itself. So, and again, that's going to ring true for a lot of this stuff here initially, where it's a lot of real basic stuff, but you need this stuff proven, because, like, you really pay attention to a lot of the things that we're going to be doing for the course. You'll be shocked how often these basic, simple things are actually used. So they really need completely convincing arguments. Otherwise, right, our whole foundation will crumble. Alright, so next up, let's now verify that following or equal statement. That, and now this one is revealing that negating flips inequalities. So if A is less than or equal to B, well then by 1, I know this has to be true. because by 1 I'm allowed to add whatever I want across an inequality without screwing everything up, and a minus a is equal to the 0 element. Alright, and then similar logic here, add both sides by negative b, and now we get negative b is less than or equal to negative a. So if I negate an inequality, it flips. And now again, like I said, we're proving this for the less than or equal to. You can get strict less than or equal to work as well. Alright, and now the rest of the proof here, I'm just going to go through quick because it's basically just repeatedly apply point 1. So start with this assumption and then now add a to both sides. Start with this assumption and then add b to both sides. And again, note where associativity is being judiciously used. So good thing we assumed addition is associative. It'd be awful if we didn't have associative things here. Okay, alright, so now that we've seen some theorems with addition and ordering working well together, let's do some stuff with multiplication. Alright, so if we know b is less than c, well then I can subtract b over. This is greater than or equal to 0. A is greater than or equal to the hypothesis, so the multiplication is greater than or equal to it. Distributivity, I can distribute the a. And remember, minus signs can be pulled out of multiplications, which we proved. Good thing I took the time to prove that, otherwise I wouldn't be able to make this conclusion right here. And then now we add this over, and the proof's done. Ooh. So here we see kind of a more non-trivial one. This point 4 here had a lot more kind of going on with it. Where we were using how adding negatives across an inequality works, invoking the distributivity, and also the assumption that a product of two non-negative things remains non-negative, or a product of two positive things remains positive. Beautiful. And so, like I said, you'll do a similar one where a is negative, so you're going to be a little crafty with that one, but not too much. Okay, so we'll continue now seeing multiplication interacting with inequalities by proving that 1 needs to be strictly bigger than 0. Alright, so by trichotomy, we just need to verify that this can't hold. Well, suppose that was true. Well, then I would have to have that negative 1 was bigger than 0. Note, negative 0 must be 0. 0 must be its own additive inverse, because 0 plus 0 is 0. Alright, but now I've got something bigger than 0, so the product's bigger than 0, but the product of two negative things is positive. The product of two minus signs cancels. 1 times 1 must equal 1, but now I've got 1 is less than 0 and 0 is less than 1, so they have to equal each other, which is contradictory. So by trichotomy, we have to have the strict inequality, and I'm missing a pause, as always. Beautiful. Alright. Yeah, like I said, no matter how many times I go through it, there's always something that slips through. But alright, so there we go. Beautiful. 0 is strictly less than 1. Alright, and now let's wrap things up by proving that if I have a multiplicatively invertible thing, 1 over it is... Did I have an A and I'm using an X now? Yeah, what's going on? I just noticed that. Interesting. Alright, is the proof all X's? Oh, it is. Alright, well, let me change those to A's and read the proof while I do that. It's an interactive video now. Alright. There we go. Alright, so again, this is a trichotomy argument, so suppose that this was less than or equal to 0. Oh, and also... Okay. Well, that would mean negative... suppose this was less than or equal to 0. Well, A is positive, so if I multiply A across this inequality, it will not change. Right, so that's a fact from point 4 here. Alright, but A times this is 1, and anything times 0 is 0, and now you've got 1 is less than or equal to 0, which contradicts 5. So it's got to be that 1 over A is positive. Strictly so. Beautiful. Alright, wonderful. So, we've got now a nice sampling of how addition works and how inequalities work in a field. Now, there was one other thing we talked about with ordered sets, and that was bounds. So let's prove something involving bounds and algebra. Okay, so for your homework, you will prove that the sum of two sets, the supremum, is the sum of the supremums. But I'll prove one that I like quite a bit. So this particular proposition is one that is very near and dear to my heart. Because it was the thing that convinced me how supremums worked. So we already set up supremums, and we did some proofs of them with ordered sets, but of course, when you first encounter supremums, I mean, I'm not going to pretend otherwise here. When you first encounter supremum and infimum, it really feels like very artificial, you know? It's very, like, why is this a thing? And it takes a while for it to get used to working with them, and it also takes quite a bit of time to actually really convince you that it's the right thing. Once we start talking about the real numbers in the next video, you'll see where supremum is really being used and why it really is as important as I'm claiming it is. But this was given to me as a homework problem in my analysis class. This was like the second week of the course or something like that. And I remember this homework so clearly and vividly because I remember, like, when I first sat down and was trying to work it out, I'm like, oh god, what the hell is any of this? But I just sat and stared at it, and it eventually, like, the internal fight in my brain happened, and I eventually got it. Because what I did and what I said to myself was, just, okay, stop trying to, like, conceptualize what this is. I'm trying to do this proof. Read what the proof's asking me to do, and then just start unraveling definitions. Right? Of course, it'd be great to have an intuitive understanding of how supremums work, but supremums themselves are a completely unintuitive thing. So trying to just rely on intuition for it is... eventually you get an intuition for it, but you really got to work with it first. And then once you do that, you kind of get it. Right, I remember very vividly, I was in the library, and I was just looking at this, and I was like, what the hell's going on? And then I just started going, all right, okay, let's think about what does it mean to be an infimum. So, all right, okay, that was the broad picture thing here. What are we actually meaning as the proof? So, we're taking a set, and we're creating its negation, which is just a collection of all things negated from the original set. Now, if the original set A is a supremum, then the negation of it will have an infimum, and the infimum will be the negative of the supremum. So, right, that makes a lot of sense, because if you just think visually what's going on, if I take A and negate it, well, I'm taking everything and flopping it over, right, I'm reflecting it, so, right, its upper bound then flips over and must be a lower bound. So, all right. It's got it, so obviously the supremum will, when you negate it, become an infimum. Right, visually, you can imagine that in your head, but right, when it comes to the proof here, right, let's just unravel the definitions. Right, don't get hung up on intuitively what this is supposed to be, and all that stuff. Just, okay, I'm trying to prove that this set has an infimum, and I'm being told what it is. So what do I need to do? Well, in order for this to be the infimum, two things need to be true. First of all, it's a lower bound, so let's prove that. Okay. So, take an element that lives in the set, I need to show that this is always less than or equal to it. Well, if x is a negative a, what does that mean? Well, that means you are negative y for some y in a. And if you live in the set negative a, then you're negative something from a. All right. A is bounded above by the sup, so I know y is less than or equal to sup a, and then flip it. We know where you're allowed to flip the negation here, so now I get negative sup a is less than or equal to x. So that checks off the first box, sup a. Negative sup a is indeed a lower bound for negative a. All right, now I want to prove it's the infimum. I got it's a lower bound. Now let's prove that it's greater than any lower bound. So again, unraveling the definition. What is an infimum? It's a lower bound, and it's the biggest one. So prove it's lower bound first, then show it's the biggest one. All right, so take any lower bound for negative a. I need to relate this to the sup of a, Alright, well, pick an element that lives in A. Its negative lives in negative A, so that means B is less than or equal to negative X. We can then flip the negation, and what do I have now? I now have that anything that lives in A is less than or equal to negative B, so negative B must be an upper bound for A. The sup of A is the smallest lower bound. So sup of A must be less than or equal to B, negative B, and then we flip the negation. All right, we negate across the inequality. The negation of a negation is the original, and now we've got that B, which is a lower bound for A, is less than or equal to negative sup A. So negative sup A is a lower bound, and it's bigger than every other lower bound, so it has to be the greatest lower bound, so it's the infimum. And that's it. Proof's over. Right? And like I said, just a simple unraveling of the definitions. Right? Just reading what we have and really thinking about what we got to do. I'm trying to prove we've got an infimum. So what does that mean? I got to prove that this is a lower bound, then it's the biggest one. Okay, and then now I'm using the supremum fact of A, specifically right here, because sup A is an upper bound for A, and then I'm using the least part here to get the inequality on the the lower bounds for negative A. Beautiful. So, right, now, I think it took me about 6 minutes to verbally walk through this proof, and like I said, I love this particular statement. It was the one that, during my second week of my analysis course, where it made soups and imps click in my head and go like, oh, that's what these things are, I get it now. Right, no, it just simple unraveling of definitions. How many times have I said that? 1,000. But, so it's more interesting, right? I very brief, right, it didn't take me too long to explain it. Now, how long do you think it took me to actually figure that out? Because it definitely wasn't 6 minutes. So when I first encountered this stuff, it takes a bit of time and effort. 6 hours is probably, that's an overestimate. I think I got it in a couple hours. But it did take some time to really, read and reread and rethink. So, right. This is not simple stuff, right? It is, right, again, mildly artificial. Supremums and infimums, I'll be completely honest, they are kind of an artificial thing. They are incredibly useful, and they end up being the key thing, but kind of at first glance, right, this just does feel like some stuff I can do. But hopefully, this proof had a effect on you, like it did me. This was this is how I know, like, I'm a weird person, I guess. This provided a very profound effect on my psyche. But hopefully it touched you like it touched me. That's a great place to end the video.